Hello everyone, and we are back to the continuation of the Laplace transform lectures, and I think today it is seventh lecture on Laplace transformation, and main discussion for the today's topic is on the Laplace transform of derivatives. Okay. So what we have done in the previous classes are that we have discussed the Laplace transformation of power function, and which is going to be very useful when it is combined with the S shifting. So that formula we have written, which is very useful to get several of the formulas at once. So that is the power of that formula. And then similarly, there is these are some of the properties, namely the Laplace transform of derivatives, and another property is differentiation of Laplace transform. So if you learn these properties, then we can find the Laplace transform of even more functions without performing the actual integration. So the point to be noted is that if you see your first lecture on Laplace transform, you've seen that calculation of the Laplace transform requires that you have to perform an improper integral and then get the answer if it converges. Now we are saying that if you know the properties, we can find the Laplace transformation without evaluating any integral. So that's the point. So right. So that means your job is little bit simplified in the sense that you are not going to worry about the evaluation of the integral. So that is the power of these properties or theorems. Okay. I am now writing two at a time, two properties at a time, because apparently it gives you confusion at the initial stages, because first and second sentence, both of them contain derivatives. These two are not same because the first one is Laplace transform of derivative of f of t. So that means you are first differentiating the given function. So the first case represents the derivative of the input signal. Input signal is f of t. This is input signal, right? You have this. This is input signal, and this will be your output signal. So therefore, the first and the second cases, these are the two properties. The first one refers to the derivative of the input signal. The second property, namely the differentiation of Laplace transform, represents differentiation of the output signal. Okay, so if you are reading the English wordings, little bit confusion may come, but once you understand mathematically, we were differentiating the input signal. That means f prime of t. F prime of t means differentiation is with respect to t. Output signal differentiation means f prime of s, but however the differentiation is with respect to s variable. So that's the difference. So there is considerable differences there. So there is no confusion arises once things are clear. Now let us see what is this property, and the property arises when we start with the defining equation. So we have the defining equation for the Laplace transform like that, and then if this is the starting point, we are asking the question, how are we going to evaluate the Laplace transform of f prime of t? Okay, so that is the first one that we are going to discuss. So I'll put arrow here. So we are discussing this one. Okay, so f prime of t is nothing but, we can say this is df by dt. So let me therefore write down this as an integral 0 to infinity. So f prime of t we can write down like this, df by dt, and then you have e to the power of minus st, then you have a dt. So like this you can write, and now you can simplify this as integral 0 to infinity e to the power minus st. Let us write down here. Here what happens is df by dt is there, here dt is there. So therefore essentially you will be getting only df, and df, just for much more clarity, let us write down that. In fact, you have to understand what do you mean by df. What is this f here? F means f of t. Okay, so f is nothing but it's a function of t. That is the meaning. So that I am writing explicitly here when this dt is cancelled. So we will be writing like this. So this is now clear that the first function can be taken as u, then this is anyway d here, and this will be your v. So you can apply the udv formula for this, so that will be convenient. And if you do that, so that gives you like this. You have e to the power of minus st, then you have f of t. So let me write down like that. So this is f of t. Here what happens is you have to apply the limits 0 to infinity. So therefore, this being the improper integral, directly it is not a tradition to write directly substituting infinity. So I should not write in infinity here, the upper limit. So for that reason, what we do is we are supposed to write 0 to some finite value r, and this r will approach infinity. Okay, so that has to be written explicitly. So I will write down like that, limit r tends to infinity. Okay, we don't directly substitute infinity here. The reason being, infinity is not a number. If infinity is a particular number, you can substitute. Okay, infinity is a number that is too large that you can't even imagine. So it is that kind of number. Okay, if you are able to write down a very big number and if you say that that is infinity, then your friend will tell, he will put an additional 0. Say for example, suppose, just for example, if you say that this is the very big number and this is the infinity, in case if you say like that, your friend will come and put one more 0 here, and he will say that I have put another number which is larger than what you have given. Then another friend will come and put one more number here, and he will tell that this is larger than what you have written. If you are going to continue like this, there is no end for that. Okay, which means that you do not know what infinity is. Infinity is a number that you cannot even imagine what it is. Such a number I cannot substitute here. So that is why, technically speaking, we cannot put in infinity as an upper bound here and then substitute directly infinity. We cannot substitute infinity directly, but rather we take the limit. That is what is called in the limit of or approaching infinity. We can only approach infinity. Okay, we can try to approach the sky, but we cannot touch the sky. That's the point, and therefore, because of that technicality, this is how we write like this. And then so this is your uv, then minus integral v du. So integral v du, so v is f of t, then du is, you differentiate with respect to t here, so I will be getting a minus s. So you get a minus s e to the minus st dt. So that completes the udv formula, and all that is the integral that you have it here. This is the integral. Fine, I will erase now. Now you keep in mind that these two are different. Later we will come back. I don't know whether we can do it today or we will do in another class. Okay, so first we are discussing on the first one. Okay, fine. Now we can simplify this. Yeah. So before simplifying, I would like to tell one important point here. The point is that if the function f of t is given to you and we are going to you are going to find the Laplace transformation upon the integral. Of course, you have the defining integral here, and then we will be ultimately getting a function of s here, and we are going to call by the symbol capital or by the function capital F of s. That's all fine, that we have already done. But then there is a requirement, okay, fundamental requirement, that what should be the nature of f of s, or we say asymptotic behavior. Asymptotic behavior means in the limit of s approaching infinity, how the function capital F of s should behave. Okay, that's called a well-behaved function for f of s. Only then we can accept that particular function as the Laplace transform. So the conditions are there. The first condition is that in the limit of s approaching to infinity, okay, so don't confuse this infinity with this infinity. This infinity is actually t. So you see that this is actually t equal to 0 to t equal to infinity. So when you are differentiating with respect to t, you get an infinity here. So that is this infinity, whatever we are discussing. What we were discussing here is, after finishing the calculation, you will be having f of s, and then we ask the question, what happens if s tends to infinity? So in that limit, how the function has to behave is that in that limit, the f of s should vanish. That means it should go to 0. Okay, so otherwise you can say it's equal to 0, for instance. Okay, in the limit of s tending to infinity, the function should behave in such a way that this number should go to 0. Physically, you can easily understand. For example, if you are going to take electric potential, and we ask the question, what should be the electric potential at infinity? I have a point charge here. You have a point charge q, and then you will be having the electric potential in the surrounding region because of the electric field which is surrounding there. So the electric field and electric potential will be present far away from the charges, and therefore we ask the question, at far distances approaching infinity, what should be the electric potential? So naturally there is a condition that we have, that the electric potential should die at infinity. That is a demanding requirement. Okay, you cannot have everything which is present all the way to infinity. So the function should, this is called asymptotic behavior of the capital F of s. The function should itself die as s tends to infinity. The same thing is true in quantum mechanics. You have the wave function, you plot something peak and then coming down like that, but the function, the tail behavior will approach infinity for large distances. The peak represents the probability. Okay, so any case in physical system or mathematical system, this is a general meaningful expression. Only then whatever expression that you are getting is a meaningful expression for the capital F of s. So this is one condition which is required, and in addition a second limiting condition is also very much required, and that is in the limit of s approaching infinity, this is only f of s. So now you can have s times f of s. S times f of s. You are going to multiply. Now you can understand what is exactly happening here. You are going to substitute infinity here, which means f of infinity. In the sense that f of infinity, as I told you cannot directly substitute. So you take the limit, in the limit of s approaching to infinity, how does this function behave? That's what it is. We are now demanding that it should go to 0. We are now demanding, or it should happen, otherwise the expression may not give any meaningful result. Similarly what happens is, you are now having multiplication here. This s itself is approaching infinity. This s itself will approach to infinity. The f of s itself will approach 0. So that means you have a quantity which is approaching infinity. You have another quantity which is approaching 0. These two are multiplied. So what should be the final result? So this should be a finite number. Generally, this is true actually. So you are literally speaking, we are not asking this question. Okay, don't get confused. We are not asking this question. S is infinity. S is infinity, and then f of s should go to 0 in the limit of s tends to infinity. Therefore you have a 0. S multiplied by f of s. So infinity multiplied by 0. We are not asking infinity multiplied by 0. We are not asking that. This is in the limit of s tends to infinity. In the limit of s tending to infinity means there is a number here. There is a number here which is very, very large, because it is approaching, right? It's only approaching. It didn't touch the infinity. So we have a very, very large number. And then you have another f of s. This f of s should approach 0 as s tends to infinity. So there is a number which is going to 0 here. So we will not say that this is exact 0, but this is a number which is approaching 0, which means, for example, for instance, I can say that this number can be very large number like 10 to the power 100. That number can be a very small number like 10 to the power minus 100. 10 to the power minus 100 is approaching 0. 10 to the power 100, you can think that it is approaching infinity. If you are going to multiply them, I will be getting some finite value which is neither 0 nor infinity. You can also say, why only 100? You can put 1000. That's fine. You can put 1000 here. But still, you multiply these two, you get a finite number. Okay, so, but then you can ask the question, why don't you put several zeros here? So as you put several zeros here, what all it means to say is, you are approaching to the infinity much more closer. In that way, what happens is, s is going to larger and larger number. This fellow will not keep quiet. When s is approaching infinity, this fellow will also approach 0. He will not stay at a particular value. Therefore, this fellow also will approach 0. So as he grows, this fellow will approach 0. It may not be equal, but they may be unequal, but the multiplication factor will give you a finite value which is not 0, not necessarily 0, and which is not necessarily infinity. So this is equal to, the first term is equal to, in the limit of r tends to infinity, e to the power of minus sr, then you have f of r. This first one, then you have a minus. So limit is over, right? So for limit case is over, then minus, you can substitute 0. If I substitute 0, basically you get a 1 here, and then this will be an f of 0. You get it like that. So that is for the first part. The second part you can simply write down. So this is nothing but the plus integral 0 to infinity s times f of t So here we are getting a situation where r goes to infinity, and then you have this function, and there is no confusion. This is much more easier than what we were thinking. E raised to the power will be dying away very fast when compared to the given function. This is what is called exponential order. Okay, we already discussed that the function should satisfy the exponential order, only then we do the calculation, otherwise we won't do the calculation. So because of the exponential order of the function f of r, this function goes to 0, because e to the power minus sr will take you to 0. So that goes out, and then so s times, this is s times, this product is f of s. Okay, that is there here. Minus f of 0 is simply there. The entire expression goes to 0. And fine, then what is the left hand side? Left hand side is Laplace transform of f prime of t. So I will write down like that. So Laplace transform of f prime of t. So finally we have like this, Laplace transform of f prime of t would be equal to s times Laplace transform of f of t minus f of 0. It is the same thing, but f of s I am again making it clear. Sorry, there is a bracket is there. It is always important to remember L of f of t rather than f of s, okay, for reasons that are frequently used, because we have to repeatedly apply this. You have to understand what it is. So it is better to write L of f of t rather than f of s, even though both are same. So this is the expression which is going to be very useful. For the derivative. Now you can repeat this calculation because you have done one derivative here. You can ask the question, what happens if I am going to perform second derivative, third derivative, etc. All the answers we can simply get it by repeatedly using the same equation. There is no need to do integration once again. So we will see now how to use the same equation to get Laplace transform of the second derivative of f of t. Okay, that's very easy. So once this is clear to you, probably I will erase this. So we will keep this one here because we are going to use the same one again and again to get for higher derivatives. Okay, so we will now ask the question how to calculate the Laplace transformation for the second derivative like that. The idea comes like this. This is nothing but the Laplace transform of d by dt of f prime of t. Isn't it? Both are same, right? F double prime is nothing but d by dt of f prime of t. So what is the advantage is that? The advantage is this expression prime here is what I am rewriting like d by dt. Okay, for convenience, both are same. Whether you write prime or d by dt, both are same. So if you want to have the d by dt version, instead of f prime, I will write d by dt. So this is your d by dt of f of t. So that is what is f prime of t. Okay, so f prime of t is what I have rewritten as d by dt. So now what we have done is second derivative is rewritten like that. This equation you compare with this equation. So if you compare like that, what happens is d by dt is there. Now what is there? F has been converted to f prime. Okay, so if you convert f to f prime in this equation, then all the thing will be converted for higher derivative. That is the meaning. So that means what? You have to change all f to f prime. Replace, this is called replacement. Okay, f will be replaced by f prime. If you do that, then I will be getting the answer for double prime. So this is, in this way we can quickly get the answer instead of going back to the UDV rule once again. So that is the point. So we will do that replacement now. So how do you replace is that this is equal to, so we are going to use this right hand side here. So let me write down the right hand side for this. This is s into, we have the Laplace transform of f will be replaced by f prime. So you write down this is f prime of t and minus f of 0. So minus, now this is here once again you have to think what is that f of 0. F of t I understand, f of 0 also should I put a prime, like that you will get a doubt. If you get a doubt like that, you have to think what is this f of 0. So f of 0 is nothing but f of t only. How do you get f of 0 means, you first write down f of t and then you substitute t equal to 0. So originally you have f of t only, in that you are going to substitute t equal to 0 and that is called f of 0. So if that is the case, f of t is replaced by f prime t, f of t is replaced by f prime t, f of t should also be replaced by f prime t. So therefore you understand that a prime will come here also. So therefore I will write down that this is f prime of 0 because of this reason. Okay, first you put f of t, then substitute t equal to 0. And that's it. And what is the left hand side? So your left hand side is this one, which is the Laplace transform of f double prime. So I got the expression for the double prime, but however let us simplify. This is not simplified still. Why it is not simplified is Laplace transform of f single prime is here, is already here. So this we have to use once again. So again you use the equation number 1 here. Okay, so let me therefore write down, use equation 1 now once again, which means in this place. Okay, in this place you have to use, and then I will be getting like this, s multiplied by the whole right hand side you write down here, s into Laplace transform of f of t minus f of 0, and then close bracket for that. Then you have a minus f prime of 0, and that's all. So we have now substituted. Now you can simplify this, which is equal to s into s and you have minus, there is one more s here, here no s, and that's all. So now you have, this is the Laplace transform of f double prime. So now this is one important result once again, which means that, so what all you have done is that you have used the equation number 1 to derive equation number 2. So only thing is, first derivative has been converted to the second derivative, which is d square f by dt square. So this is called repeatedly using the same equation and then getting the expression, which means that the clear meaning is that why only second derivative. Okay, you can also go to the third derivative, fourth derivative, etc. You can keep on doing and all the way up to n number of derivatives. So you have to repeatedly use the same formula once again, etc. But there is no, it looks like little difficult, but however there is a nice pattern coming into picture, and therefore the entire equation looks very simple. We will understand how this is simple. There is a second derivative, there is a s square. So second derivative means power is 2. So s square, if you are going to start with s square, then you reduce the power. S square, s to the power 1, s to the power 0. So once you start the power, then 1, 1, 1 you reduce, and then you keep on writing that expression. That is one pattern, which is very nice. The second thing is, once you write down the first term, all the remaining terms have a minus, minus, minus. You keep on putting minus. So therefore that is also comfortable. And second thing is that you once only one time f of 0 will come. At all the remaining places you will be getting the higher derivative 0. So this pattern comes nicely. First derivative, second derivative, third derivative, etc. And because of this nice pattern, you can also easily remember and write down. So you don't feel that it's a difficult expression. So therefore I will now write down what is the Laplace transform of d to the power n, that means nth derivative of f of t with respect to t. So n number of times we are differentiating. We can write down very easily based on this pattern. The pattern is easy. Nth derivative, so you put s to the power n, and then the Laplace transform of the function f of t. And that's all. That is the first term. Once you finish the first term, all remaining terms are minus, minus, minus. So therefore you put a minus there. Then you reduce the power. S to the power n. You put s to the power n minus 1. Then you have to start with, hereafter you have to start with f of 0 and primes. So therefore you put f of 0, then again minus, again reduce the power, s to the power of n minus 2. Now f is over. Now you put f prime. So f prime of 0, then once again minus, s to the power of n minus 3. Then you put next derivative of 0, then again minus, you reduce the power, s to the power of n minus 4, put next derivative, minus, like that it keeps going. Okay, it keeps going. But then you ask the question, is there any end for that? Do you have any end? Yeah, you have the end, because when you keep on differentiating this and then substituting 0, the situation will come where the whole expression comes to an end. So therefore what happens is, the last term will happen. I will tell you where the last term happens. When you have this second derivative, you can see how to end here. The ending point you can understand here. If you have the second derivative, first derivative is the end. If you have second derivative, first derivative is the end. That means one number less. So this is nth derivative. Therefore where it will end? It will end in the one derivative which is less. That means n minus 1. So I can now write down that this is f n minus 1. So what is the meaning of this bracket n minus 1 is, n minus 1 number of times I am differentiating, the value is 0. So that is the answer. And for the last term you don't have s here, because s is already reduced and became s to the power 0. So there is actually s to the power 0 here. So that's why I didn't write like that. So the place where you have to stop is, if it is n here, you have to put n minus 1. That is the last number that you stop. And then from here to here is the expression. So this is the expression. We are not going to, actually we will not use the nth derivative. It's only for mathematical induction. That means keep on repeatedly doing that. Practically we are not going to use nth derivative for practical applications. For instance, if you are going to use LCR circuit, you can use LC circuit or RC circuit or LCR circuit, and then you get a resonance. And for that LCR circuit, you must have seen the differential equation. What is the equation? It happens to be a second order differential equation in time, right, with the appropriate LC constants, etc. And then you have the resonance condition. Ultimately, the differential equation is second order differential equation, which means that you are going to get d square f by dt square, second derivative. So practically, going to n number of derivative, we don't really use it. It's purely for mathematical reasons. And for practical purposes, you may encounter fourth derivative in the case of bending of beams. Okay, you take a scale, you take 1 meter long scale and put a weight, and then light little deflection will be there. Okay, and then you try to calculate the Young's modulus, bending moment, etc. That experiment if you are going to the theory of bending moments, there you will be getting fourth derivative. Fourth derivative means d to the power 4 here, n equal to 4. And that's all we use in physics, and mostly we are not going to use n greater than 4. So that's the point to be noted. Therefore, what happens is, first derivative, yes, we need it. Second derivative is the majority. In majority of the situations, we'll be using the second derivative. And just for mathematical reasons, third and fourth derivative is sufficient. So practically, we will not use very high number of n here. So that is the point that you have to remember. This is only to understand how a number of derivatives you can use it. That's all about it. Fine. And then how do you understand? Okay, let us come back and then ask the question, what is the meaning of f of 0 and f prime of 0 here? The meaning is clear, that f of t at t equal to 0. Now, physically, what is the meaning of t equal to 0 is initial condition. You start the experiment and then you have a stop clock, and then you start the stop clock. So the stop clock will start running from 0 onwards. So at time t equal to 0, if you are doing some chemical reaction, the reaction will start, and then some concentration will keep on changing, and the concentration will be a function of time. So your understanding of t equal to 0 is that at time t equal to 0, what was your original concentration? How did you start the experiment? That is called initial condition. So therefore, when you see an f of 0 here, the meaning is, what is the initial condition that you are going to use in your experiment? So that is a number, so it's a meaningful number. So that is the first point. So f of 0 is not something confusing to you. That's clear. But then what is f prime of 0? Sometimes this confusion will come. So I will erase this. People, I know many of the students get this doubt. Okay, people think that if f of 0 equal to 0, then, okay, it's not necessarily 0. Let me tell you some constant. It's a constant, no? F of 0 means, you just now I told you, initial condition. At initially you keep some concentration, initially you keep some velocity. Velocity can be 0 also, that is a different story, but in general a constant velocity can be there, a certain value of concentration can be there. So any constant is okay, constant can also be 0. Okay, so if f of 0 is constant, okay, then the doubt that comes into picture is, f prime of 0 will be 0, because people think, okay, many of the students think that you're actually differentiating this one, which means that I am differentiating the constant there. So this has to be 0. Like that, students will get doubt. And as I already told you, this is not necessary that it has to be a constant. In many cases, you can also have 0 as the initial condition. Okay. In many of the situations, you don't initially put initial velocity. Initial velocity may be 0. For example, take this example. I am holding this chalk piece here, and then I can simply release my hand, and then this will start falling down. So when I am releasing my hand, I will start the stop clock. At the same time, what is the initial speed I have given to this chalk piece is 0. I did not give any speed. Okay, all the speed is because of the gravity. So therefore, this 0 is also a meaningful number to start with. Now the question is that if f of 0 is 0, f prime of 0 should also be 0, because I am differentiating this. If you differentiate 0, I am getting 0. Like that, the doubt comes. But the answer is this. This is the answer. Okay, 0 may be a special case, that's all fine. But in general, in most of the situations, remember that if f of 0 is equal to 0, then f prime of 0 is not necessarily 0. This is very important condition. The reason is, as I already told you, the reason why the confusion comes is, we are not differentiating f of 0. That is where the confusion comes. We are not differentiating f of 0 to get f prime of 0. Then how are you getting f prime of 0? So now, therefore, now you understand this. Let me erase this. You have to understand what is the meaning of f of 0. F of 0 is nothing but f prime of t. There you substitute t equal to 0. So I am not differentiating 0 here to get this f prime of 0. Then what are you doing? You go to the original function, perform the differentiation. That differentiation will be a function of t. In that t you substitute 0. There is no guarantee that 0 will come. Okay, therefore, what happens is, if f of 0 is 0, then f prime of 0 need not be 0. And therefore what happens, you see that this is f of 0, this is f prime of 0. We are not differentiating this and putting here, because f of 0 is actually a constant. If there is a constant here and then your derivative should be 0 like that, if you think, then the whole terms are 0. F double prime, this is triple prime, right? So this is triple prime and so on, right? So none of them is 0 unless special situation. So this is one place where many students ask the doubt that it can be 0, but this point to note down, it need not be 0. So keeping these points, the equation is very meaningful, because this represents the initial conditions, and then here you have one initial condition, only f of 0. You see this, only one initial condition. If you are looking at equation number 2, there are two initial conditions are there. One initial condition is f of 0, second initial condition is f prime of 0. Then you ask the question, why do you want two initial conditions? Mathematical theory clearly tells you that if you are going to have second order differential equation, you must require two initial conditions. It may be initial or boundary, but whatever it is condition is required. If you have a first order differential equation, one initial condition is required in order to fix the arbitrary constants. Fixing means finding the arbitrary constants. Arbitrary constant means constant of integration. Okay, when you are putting the integration, one constant will come. So similarly, when you are dealing with the nth order differential equation, you need n number of initial constants are required. And where are the n number? N minus 1 number is there because of derivative, and only 1 is there without derivative. This is the one, right? This is the one without derivative. So n minus 1 of them are there with the derivative, one of them is there without derivative, total number is n number. So therefore it has to be there, otherwise the differential equation is unsolvable, in the sense that you cannot fix the arbitrary constants. So this is the overall idea about the Laplace transform of derivatives, and the purpose is very clear, right? The purpose is, why do you want to do all this calculation, is that we are interested to solve a differential equation like that. Anything is okay. Just for example, I am writing d square theta by dt square plus some constant k into theta equal to 0. So if you are going to have this equation, this is a second derivative is there, so you have to use the equation number 2. Okay, if third derivative is there, you substitute 3 here and then do it. That's all about it. So once you have this equation for simple pendulum, or just now I said that LCR circuit, you write down the equation, it is a second order differential equation. Forced oscillator, all our second order differential equations will come. So essentially the purpose of learning Laplace transform of the derivative is that we can apply to this differential equation with constant coefficients and then get the solution. So this is a primary objective. But the only difficulty, or there is only a small restriction about the Laplace transformation, is that most of the time this is applicable only for constant coefficients. Okay, so you cannot have some variable here. Constant should be there. So that is one requirement which is going on. So that restricts the number of differential equations that you can solve. So this is the reason why I told you in the beginning of the class also that you cannot solve every of the differential equation using this Laplace transformation, but only some collection of differential equation can be solved. But at the same time, whenever you are able to solve this differential equation, they are very comfortable and elegant, okay, when compared to the methods of calculus. So in that way, we prefer this method of solving the differential equation. So that is the ultimate conclusion. We will start with some equation and then solve the actual differential equation probably in the next class. Okay, fine.